Okay, thank you very much for the introduction, and I will continue yesterday's talk. So today I'm going to talk about some review for the shift operator or cycle representations, and then make some precise conjecture about reduction, some quantum cohomology of the reduction. So in the spirit of Telma. So let me just briefly review. Maybe already many people have already explained what is quantum connections or F-bundles or quantum D-module. But I just try to explain again, and there's some slight difference because in my case, I'm working on equivariant quantum connection. So quantum D module, I'm going to talk about quantum D module. So quantum D module, let X is again smooth projective right E with the action. For us action, TC now is C starts to L. Yesterday T was just S1 to the L, but today TC. And then I have this Novikov ring, Novikov ring. So I'm going to use a Novikov ring with multi-parameter Novikov ring. So this is a completed group ring of the monoid of effective classes in second homology class of X. So I write any subscript n of X. So so this is just a set of effective curve classes. Maybe you could maybe even restrict to rational curve classes. But and then you have arbitrarily sum with coefficients in C, and AD is a coefficient which is in C. And maybe you can actually I just here use this C coefficient, but you can replace C with any group. So group mod group double bracket Q means something. So you can define this. So this is my Novikov ring. And quantum equivariant quantum cohomology is maybe similar to quantum cohomology. This will be so this is some vector space equivariant quantum. This equivariant cohomology is infinite dimensional vector space of a C. And you adjoin Q and tau. So Q maybe Q is, as I said, this is Novikov variable, and tau is some new variable that some I call bulk deformation parameter, which lies in again infinite dimensional parameter space, equivariant cohomology of X. So yeah, in the ordinary cohomology case, non-equivariant case, this is a vector, finite dimensional vector space, but now it is infinite dimensional vector space. So there are several options here. So one option is, for example, you can think of this as a finite rank module over equivariant cohomological point. Then you can think of this as being parameterized by finitely many parameters. That I think is standard way. But on the other hand, because I'm going to also use shift operator. Shift operator is not linear over the equivariant cohomological point. So sometimes I also need infinitely many C bases. C basis, this is an infinite dimensional vector space over C, and we need sometimes C bases. That depends on the situation. And this quantum product, yeah, so this quantum product is, I think, is a standard definition, just replacing the Poincare pairing with equivariant Poincare pairing, and this is equivariant graphic invariants. And even so, equivariant gets you this star is a supercommutative and associative multiplication. And our main object of study is this quantum D module, which is defined to be somehow form for series in Q and tau with coefficients in this module. So this module is again polynomial in Z with coefficients in equivariant. So Z here is another parameter. Yeah, in maximum stock is Z is my Z is the same as U. Was U in the previous talk. And yes, and I have several connections. So there are connection. I have three kinds of parameters: Z parameter, Q parameter, tau parameter, and Z parameter. There are connections in the three variables. So I have a connection in Q direction. This is a logarithmic connection, and connection in tau direction, alpha, and the connection in Z direction. Maybe the formula already explained in many other talks, but maybe let me mention something. So yeah, so here I have this now, for example, in the Q direction. There is some slight difference, maybe not so much important, but I have a connection in the H2 equivariant H2, so not just ordinary H2, and right, as I said, I need to use a C basis instead of basis over equivariant homological point, and then this will have some infinite many parameters. Even though we have infinite many parameters, there is no problem in the definition at least. And we can just define these connections on an infinite dimensional base. Maybe another reason I need this infinite dimensional base is that maybe later you consider the reduction of X, a symplectic quotient of X, and then you have power math, and depending on the size of the cohomology of the reduction, somehow, yeah, somehow you need to choose C basis, because perhaps you can choose some basis on equivariant homology that project to a basis of the reduction, the cohomology of the reduction. But of course, the rank of the reduction changes. So if you change the stability condition. So yeah, so somehow at this point it is most convenient just take arbitrary C basis. So yeah, there's some technical differences that I take. As I said, I take equivariant second homology class of Xi, and then let Xi bar will be the image of Xi. So this will be a non-equivalent limit of Xi. And then derivation term will be only depend on the Xi bar. So this is just defined by this formula. It's just simply formula. So yeah, just acts as a logarithmic derivative. And yeah, all the vector field is similar to the other case, but except that I have infinitely many bases, so yeah, this alpha, the sum of alpha is infinite. And there is a grading operator mu. Mu is yeah. Here there is some. This is the reason why I need the infinitely many bases of a C, because this mu operator is not linear of a C lambda now. Because multiplication, if you multiply by lambda, then it changes the degree. And there's several remarks I wrote below. So I use, maybe as I said again, I need to use infinitely many parameters. And also, this will be important in the later application, but I can work with graded completion. So because of the grading axiom in quantum theory, every, for example, these connections or quantum products are all homogeneous with respect to a certain degree. And for instance, maybe the degree of tau alpha will be 2 minus degree P alpha. P alpha is a basis of the tau alpha. And degree of Z is 2. And the degree of Q to the D will be 2 times Gaussian class dot D. And so maybe what I want to say here is that I can work with graded completion. So you can work with maybe, for example, yeah, I was saying this kind of formal power series ring, but this formal power series ring is not necessarily arbitrarily formal power series, but we can think finite sum of homogeneous formal power series with respect to this degree. And finally, there's an ingredient here for pairing. The pairing is just defined by this formula. So this on the right hand side, this is just equivariant quantum pairing, but I need to flip the sign of Z. So in order to have the compatibility with connections, so then it will be compatible with connection. So in other words, it is flat. Pairing is flat with respect to the connection. So this is just an equivariant extension of the F bundle or quantum key module in the non-equivariant sense. And on this module, I have a shift operator. So let us move to the definition of shift operator. So yesterday I explained that the shift operator comes from co-character group. So so you have a co-character, so homomorphism from S1 to T. Then this induces a map on the loop space. So this is just given by this formula. So mapping loop to the by pointwise multiplication of the character, you get another loop. So this is a lattice action, co-character lattice action in the loop space, free loop space. So LX stands for the free loop space. But some of the issue here is that actually maybe I recall that this quantum cohomology is meant to be the semi-infinite cohomology of the universal covering of free loop space, not just free loop space. So I need to lift this action to universal covering of free loop space. But if you think a little about this, then maybe you find that there is no canonical lift of this action, of this map, of this action to the universal covering. So of the free loop space. So actually, you also need to extend the lattice, and extension is given by this exact sequence. So the exact sequence is something standard exact sequencing, which comes from Sever spectral sequence for the Fourier construction, which actually turns out split in this case, and it will be a short exact sequence. And I have this short exact sequence. And the left side is, this is just a second ordinary homology of X, which acts on the free loop space, the universal covering of free loop space by deck transformation. Maybe I should say that this is H2 will be identified with pi1 of free loop space, assuming X is simply connected. Then this H2 of X will be pi1 of Lx, so this will be acts as a deck transformation. And the left rightmost, this one is the same as a co-character. And as I said, this acts by Seidel representation. Just this way. Ready? And actually, if you consider the universal covering, you can show that this middle group the equivariant, second equivariant homology will act on the LX theory. So there's some combined action. Maybe I'm not going to use floor theory definition, so maybe this doesn't really enter into the definition, but maybe this gives you a reason why I need to consider the action of its second equivariant homology. And there is one, yeah. So maybe, yeah. Maybe before this remark, I can say. So the leftmost group, this is a deck transformation, and this corresponds to the Novikov variables. And as I said, the right one corresponds to the Seidel operator. And so we can naturally consider the combined action of the Novikov parameter, and Seidel parameters. And so in the end, what I'm going to define will be a combined action of second equivariant homology on quantum equivariant quantum. So yeah, so far, so this is motivation for the definition. And there's also another slightly technical point, and this is a difference between homological homology, homological H2, and algebraic cycles. So maybe I can consider the subgroup of H2 formed by algebraic classes, or maybe rational classes, and then you can show that actually you can show this exact sequence, some analogous exact sequence, analogous to this, but just restricting to algebraic classes. So what I'm actually going to define will be an action of the middle group. So equivariant N1, I don't know how to call it, but okay, so so with this motivation, I go to the actual definition of shift operator or Seidel representation. So so Seidel representation in our work, this will be defined by counting holomorphic sections of the following vibration, EK over P1, is called Seidel vibration sometimes. And EK is defined as follows. So K is, sorry, maybe I say K is a token of T. EK is a quotient of X plus C2 minus 0 by this equivalence relation. So this is some twisted bundle, X bundle over P1. Because if I consider the quotient of C2 minus 0, this will be P1. And yeah, so S acts by S to the K on X factor, so it is not trivial bundle. And S to the K is K image of the co-character of S. And maybe if you haven't seen this Seidel space, maybe I can explain a little bit about the geometry. So this EK, the Seidel vibration, can be viewed as gluing two trivial X bundle over disks along the boundary of disks by, so this is just, you can think of these as a trivial X bundle over disks, two disks. And then you glue by this map phi. So this is a clutching function of the fiber bundle. So it's sending X EI theta to K e to the minus I theta dot X, comma e to the minus I theta. So somehow this is just twisted by the action of K. So this is just follows by the definition. This just follows from the definition. And you can see that maybe I want to count sections, holomorphic sections of this Seidel vibration. And so I want to count the map, count holomorphic sections. Maybe briefly I consider just a moduli space of such holomorphic sections, and then evaluate at 0 fiber, infinity fiber. And then you have some correspondence between cohomology of 0 fiber and cohomology of the infinity fiber of both X. So that is a Seidel operator, actually. And so here, I'm going to say the sections of EK is the same thing as giving two disks, maybe if section is holomorphic, then two holomorphic disks in X whose boundaries are related by K, action of K. So so this is compatible with somehow explanation in terms of free loop space. So as I said, Seidel representation comes from the map between the loop space and actually, so counting holomorphic sections of Seidel vibration is something like considering an action of K on a free loop space. So yeah, so this is a Seidel vibration, and actually, so maybe I want to think of this Seidel vibration as a finite dimensional approximation of the Borel construction. This is what I do next, what I explain next. So I have some fiber diagram in the category of topological space. So I have this Borel construction. Borel construction is just X crossing T modulo T and mapping to BT. So this is some topological space and vibration. And EK over P1, this is an algebraic thing, but you can consider some map from the base. You can embed P1 to P infinity, which is BS1. And BS, somehow K is a co-character, so it's a map from S1 to T. So you can take a BK, and then you can take a map from BS1 to BT. So K induces a map from BS1 to BT. And it turns out that EK, this Seidel vibration, is a pullback of this Borel construction. And this says the following. So you can maybe, I want to somehow count curves or sections of this Seidel vibration. And the curve class in this Seidel vibration is actually can be viewed as an equivariant homology class. So if I consider the sections of EK, then this defines an equivariant class in second equivariant homology of X, because considering section here will give by composing this map. You can think of this as a second equivariant homology class. And this second equivariant homology class will, after projection, will be just given by this BK. So therefore, this lies over K. So BK first again gives some second homology class of BT that is identified with K itself. So yeah, so this is somehow convenient way to parameterize the homology class of sections for all K. So actually you can move K, you can vary K, and this will be parameterized by a single group. So this just single group, second equivariant homology. And depending on some of, so there is a natural map from second equivariant homology of X to second equivariant homology of point. But depending on somehow which point so that class in here lies over, you can tell which somehow side of space you're using. And this side of space has some action, torus action, T hat C, right? T hat C. And maybe this explains the origin of the parameter Z, another parameter Z. And I have the following action, lambda comma Z, act on on this side of vibration by this map. So this is basically lambda is an element of T and Z is an element of C star, but lambda acts on X, the fiber X, basically fiber, and the C star part acts on the P1 part, just rotating basically. And if you look at the fiber at 0 or fiber at infinity, and fiber at 0 and fiber at infinity are both canonically identified with X itself, but you can just compute this action and show that they have this action. So on fiber at 0, T cross C star acts by the projection to T, so just the action, ordinary the action, and on the infinity fiber, the action will be slightly twisted by the K direction. So K is a co-character in T, so you can twist like this. And yeah, this is somehow trivial identification, but maybe important technically somehow. There's some canonical identification between the cohomology of the 0 fiber and the cohomology of the infinity fiber, because they are in the end the same space. So, but they are the same space, but they have different cross action, T cross C star action, T hat action. So, so this is maybe similar to what I said yesterday, I guess. So this is not equivariant in the ordinary sense, but equivariant with respect to group automorphism of T hat. So therefore, I have a formula like this. So where F lambda Z is any element of polynomial algebra in lambda Z, which is the same as equivariant homological point. T hat equivariant. So here you see some shift of the equivariant parameters. And so I give you a definition of shift operator, which looks a bit complicated, but maybe philosophically it's not so complicated, but just formula a bit complicated. So I take any element beta, which is in the algebraic version of equivariant homology class, second equivariant homology class, and set K to be the minus of the beta bar. So beta bar means the image of beta in second equivariant homological point. And then I define S hat beta. So hat indicates that I'm combining notebook parameter and the side of representation. And I define this S hat beta by this formula. Yeah, so maybe C0 and C infinity are just element cohomology of T hat equivariant cohomology of X0 and X infinity respectively. And this is a map, self map. So this S hat beta is a self map. So this map from homology of X0 to homology of X0. And so first I take identification phi k, and then this will be an element of homology of X infinity, and then take a pairing with C infinity, which is an element of equivariant homology of X infinity. And this will be given by this formula. This is just equivariant Gromit invariance of EK. And yes, maybe a little bit complicated, but tau, yeah, sorry, so this tau will be originally just homology, equivariant homology parameter X. And I need to take a lift. I need to take a lift of tau to an element here. So the equivariant homology of EK. So the side of vibration is tau. But there is such a unique lift such that restricts to tau on the zero fiber and restricts to phi k of tau at the infinity fiber. So I can take that things. And then you count sections. This is a section class d minus beta, which lies over k, and because I said k is minus beta bar, this class lies over k, and therefore this corresponds to section class of ek. Yes, somehow this is a bit complicated, but basically just counting sections of cycle calculation. And the claim is that these operators satisfy this shift operators satisfy the following properties. So the first property is, I think, is obvious from the definition because of these pk things. And yeah, so I mean, if I don't have these pk terms here, then it is just linear or equivariant homological point, but otherwise, so because of this factor, because of pk, I have this property. And there's another thing. So this S hat beta does not necessarily preserve this quantum D module itself, meaning some of the positive parts is in Q. So it may involve some negative parts in Q. So maybe I don't explain this notation, but there's some sigma 0 minus beta bar, which is a piecewise linear splitting of yeah, it's a linear splitting of this inclusion. And oh, maybe I'm sorry, maybe I'm confused here. So this is not this map, sorry, this is not this map. Oh, it's not this map, but this will be a map from second equivariant homological point. And the natural map is this direction. And I can take a splitting here. Okay, so there's some splitting, nonlinear splitting given by geometry, so-called minimal sections or maximal sections. And yeah, and so maybe I didn't explain, but this is just a monomial in the Northcote variable, and it may involve some negative parts of Q. And this S hat beta is equal to Q to the D if beta is an element of N1. So not non-equivariant one. So N1 is contained in N1 P of X. So yeah, I define a shift operator for any beta in here, but if beta happens to lie in N1 of X, then it's just a knock-off factor. And I have some standard Seidel representation property. So then I have some fundamental solution of these structures. So so quantum D motion now has three kinds of connections and shift operator. And then I can introduce there's some well-known fundamental solution defined by this formula. So this here I need to use X. So this is again defined in terms of equivariant quantity variance of X and descendant invariance. And I somehow, by expanding this correlator in this infinite product, infinite geometric series, I see that this fundamental solution only contains negative parts in Z, and can be, and with coefficients in equivariant homology, non-localized equivariant homology. So there are two somehow, yeah. yeah, there are 2 points of view. So one point of view is that you can consider this as a formal first series in Z inverse, and with coefficients in the equivariant homology of X without localization. The another point of view is that if you look at any coefficients of this monomial, then actually it turns out that this is a rational function of the equivariant parameters lambda and Z. This follows by the partial localization formula. So yes, this is somehow a very useful fact, and it is related to the properties of this fundamental solution. So this fundamental solution, I call this fundamental solution because of the following property, and this is known by many people, solving diagraph given down for the differential equation part, and the Okongo-Panta Haipande and Morito-Kongo, Braverman, or Morito-Kongo. And those people have shown, yeah, so the first 3 people show these first 3 properties. So, and the Okongo-Panta is for this shift operator part. And the first 3 just say that these quantum connection, this is non-trivial connection, will become trivialized, will be trivialized by this operator M, like this. This operator will become something trivial operator, not completely trivialized. So if there's no this term, then if we don't have this term, then it will be completely trivialized. But you could do that, but maybe I don't do this here. You could also eliminate this term as well, but no, we are not going to do that. And in addition, this shift operator is also somehow trivialized by this fundamental solution. So this curly S hat beta is some combinatorial operator, hypergeometric operator given only by classical cohesion. So you only need to know the normal bundle of the fixed loci, and you don't need to count curves to define this operator. This operator is purely defined in terms of classical cohesion. And maybe I give you the definition below, but maybe this definition looks a little bit just complicated. But so this S hat beta, this will be an operator acting in T-hat equivariant homology of X localized. So this is just T-equivariant homology of X answered with these rational functions in lambda and Z. As I said, this M, fundamental solution M, is actually defined over rational functions in lambda and Z, so this makes sense. Also, these compositions make sense. And this operator S hat will be defined by this formula maybe here. This is some hypergeometric type of factor. Somehow most of the factors will cancel. All but finite remaining factors will cancel out. But here, this rho F alpha J arises from this normal bundle of F inside X. Sorry, so maybe I should say that F is a T-fixed component. F is a T-fixed component. For each T-fixed component, I have a T-weight decomposition of the normal bundle. And then I have Chern roots of each bundle. It's normal, so eigenbundle, so the eigenbundle of the Chern roots. And then somehow this will be defined this way. Okay, and some of the definition is something like you take any element F in the localized equivariant homology, and then you somehow restrict to F fixed locus, And then somehow equivariant parameter will split off. So this will be just a function of lambda and z with values in the homology of f. So you can shift equivariant parameters by this. And then apply this hypergeometric operator, and then apply some monomials of Q, which I don't explain. And one remark about this operator is that this S hat beta can be further trivialized by the equivariant gamma plus. And so actually this, maybe you can think of this factor as arising from the difference equation satisfied by the gamma function. So I'm not going to describe what is the precise formula, but what I'm going to say here is that maybe if I further somehow consider something like gamma at inverse, it's not quite correct, but if I consider some equation like this, then this will be somehow something like almost this is not correct. This is not correct, but it is almost like this. So if you conjugate this operator by gamma plus, then it will be actual just only shift operator. Maybe possibly with some powers of t. But this formula is not quite correct. So roughly speaking, and yeah, maybe I should also mention something about given tau, and because this will be necessary for the formulation of the reduction conjecture. And given tau is some cone inside this equivariant homology, so localized equivariant homology. So maybe this lies in there. Right here. So this is a union of images of these fundamental solutions. And this is some infinite dimensional submanifold, Lagrangian submanifold inside some infinite dimensional space. And you can think of this as a graph of df0. Maybe I'm not going to talk very much about this, but you can think of this given tau as a geometric version of quantum B motion. And what is non-trivial here is that this Lagrangian cone is preserved by, maybe first of all, it is preserved, should be preserved by because of this commutation, so of these fundamental properties of this fundamental solution. Because the operators on the left side will somehow preserve the quantum D module. For instance, maybe this operator will preserve the Lagrangian cone in a sense. So and similarly, so this is S curly S operator, shift operator on the given tau space. This also preserves the given tau cone. So this is some non-trivial property. And for example, maybe it's surprising because this shift operator itself, maybe you can see from this formula, seems to contain a lot of rational functions. But for instance, a point on the given tau cone, for example, this should be, for example, this expression itself is regular at lambda equals 0. So it is defined without localizing lambda, for example, if you expand at z to infinity. So if you think of this as a formal course, it is inverse. It is regular at lambda equals 0. And this regularity is preserved, to be preserved by application of curly S. And that is quite an integral property and sometimes quite useful in determining this given. Anyway, so far this is only review for the shift operators. And then maybe I go on to the formulation of the reduction conjecture. So here I'd like to assume that the generic stabilizer of T action on X is finite. Consider this situation. And by the definition of S hat beta I gave above, then there is some monoid, some explicitly described monoid. I didn't explain what is sigma zero. This is something called the minimum section, maybe maximal sections. And but there's some, this is some nonlinear splitting, maybe I mentioned briefly. And there's some extension of the cone of curves to the equivariant setting. And so, yeah, this is a cone of curves inside N1T of X. So it has two offsets. So this is some monoid inside equivariant curve classes, which somehow extend the original Mori monoid cone of curves. And yeah, the subject here is joint work with Mikiko Sanda, and yeah, so there is some cone, something I would call equivariant Mori cone, and if this class beta is in the equivariant Mori cone, then S hat beta preserves the quantum beam. So this is some very simple statement that you can just deduce from the definition. And therefore, this implies the following very simple proposition: quantum D module of X is a module over this ring by a shift operator. So this is maybe originally this will be just a module. I was thinking this is just a module over C I join Z and double bracket Q module over this ring. But now I can extend this to bigger mono. And because of the shift operator. And I need to somehow use this graded completion, otherwise maybe there's some problem about convergence. And the following lemma is maybe very easy, but I'm not sure if that's been known or not. But if you consider this equivariant Mori cone, it's just I can just extend the scalar from n to r positive. And then dual cone of this equivariant Mori cone, the dual cone of equivariant Mori cone is the closure of the T ample cone, known in the context of GIT quotients by Dolgachev and Ku and Tadeusz. So let me just recall what was the equivariant ample cone, the T ample cone. So T ample cone, CT of X. This is a cone spanned by the equivariant version class of T equivariant ample line bundle L such that whose stable locus is non-empty. So this is somehow the cone such that you really care in GIT theory. Cone of line bundles, ample line bundles set. Maybe I can. And this has some chamber structure depending on the on your GIT quotient. So here is a picture. And yeah, so you have some ample cone here. Ample cone, and this T ample cone is fibered over this ample cone, the non-equivariant ample cone. And if you fix some ample class omega, and its fiber will be the moment polytope of the exon. And it will be divided into chambers depending on which the GIT quotients. So so maybe altogether you get some division into chambers. So somehow this subdivision is relatively rational polyhedral. So the ample cone may not be rational polyhedral, maybe very strange sometimes. But so in the vertical direction, this will be rational polyhedral. And yeah, maybe recall that I just said that this quantum D module is a module over the completed monad ring of this equivariant Morricone. And equivariant Morricones, the dual of the equivariant Morricone is this T ample cone. And T ample cone has this kind of fan structure. Therefore, you can regard this quantum D module. You can put somehow this triangulation, this subdivision, so fan structure can be, you can construct somehow toric variety associated with it, and then you can think of this as some desingularization or some partial resolution of the spec of this field. So therefore you can regard this equivariant quantum D module as a sheaf of the toric variety associated with this fan. And so in this picture, I just draw some dual pictures, in the standard procedure in toric geometry. So if we have a fan, and then you can draw some dual polytope. And then this toric variety is this singularization or resolution of this partial resolution of this spec of something. This one, okay. And then for each somehow maximal cone C1, Ci, there corresponds some limit point or some torus fixed point of the toric variety. And so you have, for each reduction, you have some cusp in these moduli spaces in this toric variety, in which I think of this as a Kähler moduli space. And maybe more precisely, I need to consider here, I just write the pullback of the quantum D module of X to this toric variety, but actually pullback is not quite good. We need to do some extension of these cusps. And then first you consider some extension across each cusp, and then completion, certain completion. Then you might expect this would be quantum D module for the reduction, that is conjecture. Because here maybe I'm using the column map. So this is the dual of the column map. So I have equivariant homology some equivariant homology of the reduction will be embedded by the dual column map to the equivariant homology. And then somehow and somehow if I consider the Morricone here, Morricone inside here should correspond is embedded into the Morricone or equivalent Morricone here. And so you can think of the coordinate ring of this toric variety as an extension of the Novikov ring for the reduction. And yeah, maybe I finish by stating the reduction conjecture in this case. So maybe this way, maybe it might be better to state the conjecture in terms of quantum D module, but maybe there's some subtlety about this extension problem. Maybe I'll talk about this in the case of blow-up tomorrow, but there's some subtlety. So I'm not so sure in general. So but instead I can state the following reduction conjecture. So let Y be a smooth GIT quotient. And let Jx equivariant. And how this will be an equivariant J function. So this is the image of one under the fundamental solution. This could be any element of equivariant given to a column of X. And then I take the following discrete Fourier transform. And this is analogous to the sum of the residues we see yesterday. So for Willingham's integral. But so this is I is this formula. So sum over beta. And actually maybe note that this is isomorphic to the second equivariant homological point, or is the same as co-character lattice. And then you take sum of it beta, and then take this shift operator action, and then I introduce some new parameter s hat. This is the new abstract variable, and then take a column. Maybe I'll give you an example. Maybe will clarify what it looks like. Then this power series is supported. The first conjecture said that this power series is supported on the column CY hat, the dual column of C1. So CY is a GIP chamber for Y. So one of CI in the above picture. And the second statement, second conjecture, that this I lies in the given dual column of Y, which is defined over the extension of the Northrop ring of Y, as I mentioned earlier. So this is some conjecture. And maybe I should say that this discrete Fourier transform, the formula for discrete Fourier transform, maybe may look a bit complicated, but this is quite analogous to the discrete Fourier transform. So you have a function of lambda, and then you sum over lattices, and then take a sum generating. So example one. So this is an example familiar example where X is just projective space, and torus T acts diagonally on X. In this case, equivariant J function is just trivial, just one. And the shift operator, curly S operator, is just given by this. This is already we observed yesterday. And then I take this sum appearing in the reduction conjecture. And then because maybe I'm taking minus k here, so this is actually probably goes to minus k, and then this will be this will be plus. And then if I apply this operator to 1, and then only denominator survives when k is positive, right? And k is negative case because k equals 0. Negative case term vanishes because kappa of lambda to the n is 0. And you can there is a power n here, and this power n, you see that the column map kills the terms with negative k. So this is a support conjecture. So the first item of this support conjecture in this reduction conjecture, saying that this is supported on some form, and actually it is supported because k negative terms actually die. And then this is maybe people familiar in theory know that this is a J function of Pn minus 1, and therefore in this case the reduction conjecture is okay. And more generally, this just holds for any representation of torus. So vector space, torus acting on vector space. So this is somehow this reduction conjecture, in this sense, generalization of given Gauss-Mirror theorem for toric varieties. And the second example is a kind of, this is maybe yeah, another way to look at the Tillman's construction on mirror Lambda-Gibson potential. But if I consider toric variety with a full dimensional torus action, then you can consider Fourier transform, discrete Fourier transform of the equivariant shape function of x. And then it turns out that it will be exponential of some function over C. Function will be some function in S and other variables. S is a Seidel variables. And actually, this should be the topologically Lambda-Gibson mirror potentials in the sense that somehow if we consider oscillating integral of this function, then you get the quantum D-module. You should recover the quantum D-module of X. And maybe I don't give you, I'm not giving you that example here, but for example, you can compute for Pn, start from Pn, then you learn J function of Pn, and you can easily recover the original well-known Fourier buffer given the potential. Okay, so